why have I been observing star clusters and how did I become interested in them? About 17, almost 18 years ago, back in 1998, I rediscovered amateur astronomy. I inherited a pair of Fujinon 10 by 70 binoculars from my brother, and I figured, why not figure out what I can observe with these binoculars, right? So, of course, I went to the best resource there is. Where? The internet. So what they, a lot of websites mention, for a beginning astronomer to do with big binoculars is observe open clusters. So this sort of segues into a story about some of my resource information. So I began researching open clusters, and one of the catalogs or groupings of open clusters are called the Colander objects. And his dissertation was on the structural properties of open galactic clusters and their spatial distribution. Okay. If you want to do some light reading, this is something you may want to look at. There's some nice statistics, there's some nice integrals and all that stuff. So I looked up as to the source of Per Colander's dissertation. Well, he was an astronomer in Sweden at Lund University. This is a fresh copy of Per Colander's dissertation. So they went back to their storeroom and they went, oh, hey, we've got a box of his dissertations. Bang, sent it to me. The pages were not even separated, so I had to use a razor blade to separate the pages. So this is one of those, oddball, unique items. So that is where my interest in open clusters began. An open cluster is a physically related group of stars held together by the mutual gravitational attraction of the stars. Okay? Now, think of it as sort of a flash mob. A flash mob of people. They're not really compressed, they're not really congested, they're just kind of floating around loosely. Okay? So, how are they classified? There's a few academic ways we can classify them. One of which was by Harlow Shapley, and he had a scheme. It was a rather simple scheme. It addresses the concentration and richness of open clusters. So there's also a gentleman named R.J. Trumpler, and he had a more sophisticated and detailed scheme, and it also adds brightness to that scheme. So here's a little bit of a the Shapley scheme is very simple. It's A through G. So you have either very loosely and irregular open clusters, all the way down to what are considered considerably rich and concentrated. And I'll show you a few examples of pretty much A through G. Now the Trumpler scheme is a little more involved. So you have detached strong concentration towards the center. You have detached with weak concentration towards the center. It's a little bit more involved, and it also throws in the brightness of your open cluster. It also talks about the richness in whether it's poor, moderate, and rich, poor, and moderate as to how many stars make up that open cluster. Now, what we'll see momentarily in a little bit is open clusters are also younger than globular clusters. So we're going to talk about a little bit about an age difference. And it's not a small age difference, it's a pretty profound big age difference. So now, how open are these clusters? As you can all see right here, what is this object? What is this asterism? It's not a constellation. What is it? It's an asterism because it's a shape in the night sky. Constellations are interpreted as being something that, oh, that looks like a unicorn. Well, this is the Big Dipper. It's an asterism that is part of Ursa Major, the Big Bear. This is actually a part of an open cluster. Okay? The Big Dipper is actually part of what's called the Ursa Major moving cluster. And there are theories that actually our sun is a member star of this open cluster that's moving around. Because if you throw in time frame, like let's say 10,000 years ago, into one of your handy-dandy astronomical software packages, that does not look the same a long time ago. That will not look the same 10,000, 20,000 years from now. They can be compact, like M67 in Cancer. What you'll notice is that a vast majority of the stars that make up the cluster are of the same stellar type. Okay. A lot of open clusters are young blue stars. Occasionally you'll see a red star sprinkled in, but usually those are not part of that open cluster. Okay. So since we're in the winter, it's the best time for us to talk about a few wonderful, very aesthetically pleasing open clusters you'll be seeing. Now, a few things as to why amateurs should observe, or amateurs should have a better time observing open clusters. They're relatively bright, they're relatively easy to find, and you don't need a gigantic monstrosity of a telescope to observe them and to enjoy them. Okay? In a little while, I'll show you a little bit of a comparison as to what equipment you need for observing open clusters versus globular clusters. Open clusters are relatively easy to observe. You have a nice set of binoculars, have at it. Okay? You have a nice, smaller Ridgefield telescope. My first telescope was a Teleview Pronto, which was only a 70mm telescope. Great for observing these types of objects. I've been at the eyepiece of my telescope and my binoculars for hours observing M45 Pleiades. I remember one night where my kids came out and they're like, "Dad, what are you looking at?" "Oh, I'm looking at M45. "What's that?" "Pleiades." "Oh, take a look." "Okay." About 2 hours later, they came out. "Hey, Dad, come to bed. What are you looking at?" "Oh, M45. "You're still looking at that?" "Yeah, I'm still looking at that." I would go between my binoculars and almost all of my eyepieces that I had. I would go from low power to moderate power, not really high power. You don't want to really crank up the power for the Pleiades. You want a nice wide view of it. Okay? It's a beautiful object. It's readily observable. It's easy to find. And as you can see, the vast majority of the stars that make up the Pleiades are blue. They're blue young stars. They're not very old when it comes to the stellar age bracket. So Pleiades are about 100 million years old, and the vast majority of them are blue stars. Two more of my favorites. M35, which is pretty much this whole area here. And NGC 2158, which is right here. This is at times classified more so as a, some people will say that it's a globular cluster, other people will just say that it's a very densely packed, densely arranged open cluster. And one of my best memories of observing these two objects is from back in about 1999, I believe it was. Pete and I were out at an observing site we used to have called Mickey Gordon. It was down out by Middleburg. Pete had his 24-inch scope out. He said, "Hey, Ed, take a look at this." I'm like, "Oh, cool." I went over and I took a look at his eyepiece. And I went, "Oh, cool, that's M35. He goes, no, that's not M35. That's 2158. Because he had his gigantic optical device. Yeah. When we were looking at 2158, because it was a larger scope with a higher magnification, it actually looked like M35. It was a phenomenal sight. All right, we have M37, 36, 38 in Auriga. They're very beautiful to take a look at, almost right overhead, almost at the zenith. As you can see, you have a variety of very open to a moderate dispersed, to a much nicer, compact object. They're very beautiful. They're also in pretty much the winter, along the winter Milky Way. So they're wonderful to take a look at also. M41 in Canis Major. All right. here you've got Sirius. We've been hearing about Sirius as a pup, and right below it is M41, right here. Now M41 is one that has it's much older. It has some yellow stars interspersed with it. It's a wonderful object to take a look at. It's readily visible. It's an easy find. On a night, we've been having some nice, cold, crisp nights. Find Sirius and come straight down south. And that's where it is. It's a wonderful object to take a look at. M44 in Cancer, the beehive, right here. And as you can see, vast majority of the stars, once again, are blue. And sometimes, if you sort of zoom out, if I was able to zoom out, it almost looks like not just a beehive, but almost like a bee, with these being the wings of the bees. Alrighty, M46 and 47. We have an added bonus in these two objects. This is M47 over here. This picture doesn't do it justice, but there's some beautiful yellow stars that are part of the cluster. Now you have an added bonus in M47, which is right here. You actually have a nice planetary nebula that's part of the open cluster. And it is, throw in one of your oxygen-3 filters in. It's a wonderful object to take a look at. It's also a relatively easy object to find, two objects to find. Sweeping down from M41 towards the east. They're beautiful to take a look at. Alrighty, we were talking about how an open cluster can be a rather dispersed open object. Colander 70. One of the Colander objects that's actually in the catalog is the Orion region around the Orion belt. Is actually considered an open cluster. So you have open cluster, you've got Great Orion Nebula, you have a lot of wonderful objects within Orion, and even within the belt. So when you're looking at the belt, you're looking at a classified or categorized actual object. Colander 7, Orion's belt. Open cluster. Colander, here's another one. 399. Anyone know which one? What the nickname for this is?
Coat hanger.
The coat hanger. This is actually a summer object, but I needed to throw it in because it's been categorized, or classified, cataloged as an open cluster. They've been able to determine that these stars are actually at different distances. It's just like you have binary stars or double stars that are not actually related to one another in a gravitational, dance. These stars are not even related gravitationally. So these stars are actually at different distances, and what we're seeing is we're seeing stars at a different distance, and they look like they're part of a cluster. These are not gravitationally related. They're not, in conjunction with one another. It looks like it, but they're actually at different distances. One of my other favorites is NGC 7789 in Cassiopeia. It's a wonderful object. It's also known as Caroline's cluster or Caroline's nebula, because Caroline Herschel, William Herschel's sister, was the one that discovered it. It's a wonderful object. When I had my smaller Pronto, which is a 70 millimeter, almost 3-inch diameter telescope. It looked literally just like a cotton ball, just a fuzz ball, perfect round fuzz ball. Eventually, when I made my way up to a larger scope, one time I had a 100 millimeter, but then I worked my way down to a Teleview 85, which is a little bit bigger, a little bit better optics. The stars actually scintillate and actually come out. So it's no longer a fuzzball. You actually are able to make out the stars of the cluster. Now there are some in the astronomical academic community that mention that in some ways it may be on the verge of almost being a globular cluster, because it's so dense and so compact, but in reality it's a wonderful, beautiful open cluster. It's in Cassiopeia. It's easy to observe. Just take a look at the W in Cassiopeia, and it's right off of one of the legs or the back of the chair that makes up Cassiopeia. It's a wonderful object to take a look at. One of the things that I'm sort of emphasizing here is the aesthetics of the objects, because even though we're in some ways we want to learn about what makes up these objects and what's, you know, some of the what are the mechanics behind it, what are the composition behind it. Part of what makes it great to observe them is how beautiful they are. It's in a beautiful part of the night sky also. It's in Cassiopeia, right on the winter Milky Way. So there's tons of other objects to take a look at while you're looking around in there. So next we're going to talk about globular clusters. Globular clusters are a spherical collection of stars. Globular, as in globe-like. They're very tightly bound by the gravity of all the stars that are interrelated within a globular cluster. And they're found in what's called the halo of our galaxies, but in the halos of galaxies. So pretty much along the galactic plane is what it's called, is where you'll find globular clusters. Here we have the Shapley classification. He did some other classification. He was an academic. He did a classification of globular clusters. Class 1 is extremely compact, very dense. Class 6 is moderately compact, moderately dense. And then like M55, what was called a class 11, there's actually 12 classes, is dispersed and not as densely packed. Okay. Now, M3 is in Canis Venatici, if I'm not mistaken. It's more of a spring object. M55 is in Sagittarius, and we're going to talk a little bit about that in a few minutes. So here are some prime examples of globular clusters. M13, the Great Hercules cluster. There are estimates that there are approximately upwards of 500,000 stars in that globular cluster. Okay. In M13, dig up the H for you, you're talking about how globular clusters are older than open clusters. M13, the estimated age of M13 is about 11 billion years old. Okay. Now, M13 is more of a spring-summer object. It's near the keystone, within the keystone of Hercules. M15 is in Pegasus. It's still readily visible now. It's a great object to take a look at. M5 is in Serpens, which is a summer, with the spring-summer constellations. It's right next to Ophiuchus. So Ophiuchus, the big, snake handler in the summer sky, that space that's right above Scorpius is where Ophiuchus is. Now, globular clusters can exist outside of our galaxy. As I mentioned, the globular clusters exist in what are called the halos of galaxies, which is pretty much the area along the center of the galaxy, along the central plane of the galaxy. Now, M55 is not considered by some to be a globular cluster of the Milky Way. you're seeing an object. There is a dwarf galaxy that neighbors our galaxy called the Sagittarius Dwarf Galaxy. And there are academic individuals in the astronomical academic community that say that M55 is actually a globular cluster in this dwarf galaxy that's next door to the Milky Way galaxy. Okay? Now, this is Andromeda G1, also known as Mayall 1. This is a globular cluster that actually exists in the Andromeda galaxy. Now, you would need some big glass to see G1, and I've seen it, but you need a bigger scope, and you need to look along Andromeda, and they've actually cataloged many of them because they've done a lot of imaging of Andromeda, and there's tons of globular clusters that ride along or light along its halo, its central area. I had a wonderful view many years ago in a 12-inch scope. It's great to look at it. There's also the Open Cluster Club, which is a great sampling of open clusters. They have the less complicated, less involved ones to more challenging ones where they say there's something there, and you're like another colander object, as an example, is at the tip, the head of the Orion, the constellation Orion. There's the 3 stars that make up its head. That's actually part of an open cluster. So you have a wide range of objects to take a look at. It's a great sampling. So you have the Astronomically Open Cluster Club and the Globular Club. Great opportunities. The Messier objects are also a great way to sample star clusters, whether they're open clusters or globulars. NGC, there's tons of them in the NGC. You can get crazy and dig up the 471 colanders, which map over to a lot of NGCs, which map over to a lot of Messier objects. So there's a lot of duplication, a lot of replication that went on. Colander's paper was written back in 1931. So there's a little bit of dated data in there. But it's a wonderful, if you want to do a different list, and you're going to jump off from the Messiers or NGCs, go ahead and dig up the colander list online. It's readily available online. Or you can send off and get a copy. There's a wonderful, great book, that is actually, the actual title is Star Clusters, by Brent Archinol and Mr. Heinzen. This is a great book. It has anything and everything you've ever wanted to know about star clusters or afraid to ask. It's all in there. Whatever you need is in that book. It's a great book to dig up. So how to observe? Equipment. Let's talk a little bit about equipment now. Binoculars. Binoculars are very good for open clusters. In some ways, they're excellent. Because for a number of them, you want a nice, wide, open view. You want low magnification in most cases, so you can take in what's around the cluster, not just the cluster itself. Rich field telescopes, like I mentioned, smaller, shorter focal length scopes like TeleVue 85, some of the stellar views, some of the scopes that are maybe in the 4-inch size with a shorter focal length are great. They're excellent for observing open clusters. You can throw in a low power eyepiece, you'll have a wonderful wide view, and you'll be bringing in more light than with binoculars. They're also excellent. They're also good for globulars. Okay? Binoculars can be good for globulars, but the vast majority of globular clusters, the really fantastic ones, will literally just be a fuzzball. They'll be around, they'll look like a cotton ball. In a rich field telescope, some of them may have a little bit of definition, but the real big guns for Globulars are larger telescopes. They're good, they can be good for open clusters, not that great. Because when you only have about a quarter of a degree view, and you're trying to look at the belt of Orion, which is almost what I believe 2 degrees, 3 degrees, you're not going to get much of the object. But larger telescopes are wonderful. They're excellent for globular clusters because what do you want with globular clusters? You want to bring in as much light as possible. Just like observing galaxies, the bigger the better. You want to be sucking in the light so you can define more. You have more definition, the stars explode in your view. Enjoy the sky. That's what I used to, my old signature block many years ago was when I post on the NOVAC email list that I enjoy the sky. That's what it's all about, is enjoying